G2, G1 whole inverse into G2. And here U2 means first what is the component for W1? That is I plus G1, G2 whole inverse into G1. It's going to be the same as I plus G2, G1, G2. Is it fine? So in this way, that is, even if you have another component, then it would be 3 cross 2 transfer function matrices, but always you will find that is this I plus G2, G1, or suppose if there is now, suppose there is a noise, eta, and here you have a sensor transfer function, G3. Then what would be that? I plus G1, G2, G3, or G3, G2, G1. Okay?
You were talking about something related to the pole in that line. I plus G2, G1 is contributing something.
Coming to that.
So then that would be three cross two.
Exactly. That is, if it is so, then simply it will be then U1, U2, U3, and in that case it will be W1, W2, W3. And now at this moment it is a 2 cross 2 transfer function mapping, then it will be a 3 cross 3 transfer function mapping. And what I said, that is, this is internally stable if this transfer function matrix belongs to Rh infinity 2 cross 2. Now what does it mean? You have to check whether these individual transfer functions, whether they belong to Rh infinity or not. That means each of them has to be, anyway they will be real rational, but the two main things you will have to check whether they are proper and asymptotically stable. Okay. So for the same example which we consider, that 1 by s square minus 1 and then s minus 1 by s plus 2, you will find one of them will become unstable. So then, that is, it belongs to Rh infinity 2 plus 2, that is, for that you have to check, or rather this is for, you have to check whether each of the transfer function element belongs to Rh infinity. Yes. Now, at this moment, whatever we learn, that is in the, with respect to the transfer function domain. Same thing we can learn in the state space also. That too we will learn. That is, if somebody asks you, that is okay, that is, it is everything in the frequency domain. But the same thing we must be able to solve in terms of state-based matrices, right? That too we need. So, but like today, I'm not going to go towards the state-based. Tomorrow we will do that. But now I'll have to define the well-posedness. So before that, I was talking about, at the beginning I said that we will learn this definition of internal stability. What is the definition of internal stability? This is the checking condition, or it's a lemma. Why checking condition? That means if somebody asks you, that is okay, how to check whether this interconnection is internally stable or not, then you say this one or you write this one, fine. But if somebody asks you, that is what is the definition of internal stability, then what would you say? Similar to asymptotic stability. If somebody asks you what is asymptotic stability, what generally we say? That is whether, that is for a dynamic system, like if you have x dot equals to ax, comma x0 not equals to 0, then asymptotic stability means whether x0 goes to 0, that means whether x0 goes to the origin as t tends to infinity, right? Here also the same thing, but here we don't have only one, we have two systems, right? So if I say that is here x10 or x20, that is now my initial condition. Suppose as a whole I am mentioning x bar 0, that is initial condition of the whole interconnection. Whether whether xt is starting from, that is xt is the state trajectory of the entire system, whether that is xt goes to 0 from x0 bar at t tends to infinity. That is called the internal stability.
Can you repeat?
Huh. That means if you had a single system, then what is your solution? X equals to e to the power 80x0, right? Then we say that is this xt. Suppose this is the state static and this is the x0. Whether it goes like that. Huh. Here also the same thing. Now x0 has become x0 bar, a bigger x0. Because now you have this, your interconnection means you have two systems, not one. So x1, 0 is the initial condition for G1, x2, 0 is the initial condition for G2. Then as a whole, if you excite the system subjected to non-zero initial condition, whether the whole interconnection goes to the origin or not. That is called, that is as if this is the asymptotic stability of the whole interconnection. That is called internal stability. Okay. Once again, that is if you extend the concept of asymptotic stability to an interconnection, not to only one single system, but rather an interconnection, then that is nothing but internal stability. So that's why, as in case of one system, we say that is whether this xt starting from x0, whether it goes to 0 or not at t tends to infinity. Here also the same thing. We will say whether that is xt starting from x0 bar, whether it will go to 0, 0 as t tends to infinity, and provided all exogenous signals are 0 for the unforced system. If I rephrase, then here we could have asked, that is, so far we have discussed everything in frequency domain, but in the definition, why I am taking the help of the initial condition, right? Internal stability means you are trying to explore the internal dynamics of the system. When we talk about the transfer function representation, it is only an input-output representation, right? And that is also the reason we have seen, that is, if there is a pole zero cancellation, then R2 Y channel will always remain Bibo stable. So only if we think about only Bibo stability, then actually a major part, or maybe if there is an unstable pole zero cancellation, internally there is a big massacre, but we are not taking care of that. So that's why there is internal stability concept, or even asymptotic stability, that is that gives more insight than Bibo stability. That I hope all of you will agree with that. That is asymptotic stability, it gives more insight than Bibo stability. Why? Because Bibo stability, it is defined only with respect to input-output connection. But asymptotic stability, it checks the behavior of the internal states as well. That's why now state is coming into the picture. Internal stability is also about, that is, what is happening internally to this whole interconnection. That's why we are like borrowing the definition of internal stability and we are applying to this whole interconnection. That is the reason why I am taking the help of initial condition. That means gradually I am migrating to time domain expression from transfer function approach. Okay, that is the reason. So for this entire thing, that is, in the next day we will see that suppose x is the state of G1, x dot, and suppose this is x1 and this is x2. So x1 is the vector, x1 is the state for G1, x2 is the state for G2. Then it will have a whole A matrix. Suppose that is a capital A bar matrix, something into x1 into x2, right? And then plus b1 into w1, w2 plus b2 into u1, u2. From now onwards, we will have this representation. right? So then that is what happens, that is, and all the exogenous signal, that is they are 0, okay? So if W1, W2 equals to 0, then what happens to the remaining part?
W1, W2 becomes 0.
If all the exogenous signals are 0.
Then it becomes AX1, X2.
And then you see, then U1, U2, they can also be inducted within the state, isn't it? Because U1 is your W1 plus Y2. Now W1, if it is 0, then U1 equals to minus Y2. And then finally, in the time domain, this Y2 would be C2X2 but plus D2Y2, right? So that means this one, Y1. So in that way, everything can be clubbed within this state A. So finally, what we see, whether this is the stateless representation of this entire interconnection, and then that is if all the exogenous signals are 0, then under that, whether this x1, x2 goes to origin starting from x0 or not. That is called internal stability. Okay?
So if exogenous signal goes to 0, won't one U2 also go to 0?
No, U1, U2, you see, that's what I
So if
tried.
you see the matrix 0, 0,
Which one? Yeah?
so the other matrix.
No, actually DCU and DCU, they are not.
This is time that is taken.
No, not only that, that is what you were also correct. So what will happen, that is in the state space, like finally this is the solution. Here if you see, that is this is the U1 and U2, they are the combination of W1, W2 with this. But this is nothing to do with the initial condition. But in the state-space domain, even if the exogenous signals are 0 but subjected to non-zero initial condition, there will be something, right? In the transfer function domain, we have one kind of approach, or rather we have one kind of expression, and in the state space we have another kind of expression. Ultimately they will become the same. Okay? So here, that is, we will derive, that is what that's what I said, that is like tomorrow, that is I will show you that what is the ABCD, what will be the ABCD matrices of this whole interconnection. Then it would be completely clear to you. Okay? At this moment here, that is I have written in the form of just open loop. If it is open loop, then W1, W2, U1, U2 both would be there. But the moment you close the loop, what will happen? This automatically the U would be inducted here. So that tomorrow we will derive. Okay? Then what I finally wanted to mean, that is this state, if it is x1, x2, whether that state vector goes to 0 starting from the initial condition under the unforced condition. Okay? That is called the internal stability. And now that is about, there is one last thing, is the well-posedness. Well-posedness last day, what did I explain? That is whether the signal exists, right? In time domain, that is whether you get a unique solution to the differential equation of the closed loop system, right? I explained with respect to differential equation. Now in the frequency domain, what will happen? You see my U1, that is this entire thing in U2 plus this entire thing into W1. Okay, so this is W2, this is W1. So W1, W2, they are like real-time signals, right? And this factor, say for example here I plus G1, G2 whole inverse G2, here only I plus G1, G2 whole inverse. That is a gain which is that being provided by these two transfer function elements. Now we have to check whether they exist or not, right? Now that is, can you comment about that? They exist means at all the frequency points, it must be a finite gain. It should not go to infinity. Then how can we regulate that, or how can we maintain that?
So we substitute the values of those G1 and G2 and then...
No, I'm asking what would be the general condition.
Like if G1, G2 belongs to that
Each
real
individual.
Hardy space, then you can say that at every point it should be bounded. like there should be a finite frequency here.
You are right, but the problem is not problem. Actually, that is if you assume that is both G1 and G2 they belong to RH infinity, then actually you cannot deal with unstable systems, right? So that's why we cannot simply assume that is G1 and G2 both of them will belong to RH infinity.
Can I
RH
say that G1 multiplied by G2 belongs to RH infinity?
that too is not. Why? Because suppose G1 is your plant or G2 is your plant. Now in most of the cases where we need controller is the plant being unstable, right? So if you have a product of one stable transfer function, one unstable transfer function, then the product will have the same unstable eigenvalue, right? So it doesn't belong to RH infinity. That is the problem. This is a matter to think. That is, you just think about like in both the cases. Like finally, we have equations 5 and 6. This is the expression for U1 and U2. Last day I said well-posedness means actually when you have this interconnection in reality, all those signals must exist. Okay, that means like if you then wish to like theoretically find the solution, then the differential equation of the closed loop system or this interconnection, they must exist and they must be unique, subjected to a unique equilibrium. Subjected to a unique, not unique, subjected to any initial condition, you must get a different output. I mean a different signal. So first of all, they should exist and it should be unique, corresponding to each and individual initial point. So now in the frequency domain, what will happen? This is the expression. This is U1 of S is this, U2 of S is that, and now where it is completely because we don't have any doubt about W1 and W2 because they are exogenous signal, real time signal, and real value. So and suppose they are bounded as well. So we don't have any issues regarding W1 and W2. But now, what kind of gain is being contributed by these elements? That is the matter of concern, right? Now we know that is both these G1 and G2, they are real rational proper transfer functions. Up to that much we can guarantee. But if you say that both of them are asymptotically stable, then that is a highly conservative assumption, right? Because in that case what will happen? We cannot deal with unstable systems, right? So in most of the cases what will happen, one of them will be your plant, another one of them would be your controller. So we do not have like any choice over the plant because the plant can contain non-minimum phase zeros, unstable poles, right? And then during the controller design we have to take care of those facts. So in the controller design, that is, it is our responsibility. That means it should be the responsibility of the control engineer to design the G2, I mean the controller, so that I plus G1, G2 whole inverse, that remains stable or that remains asymptotically stable, right? Now, if it is so, that is why I am saying that, that is, if you can at least guarantee that is I plus G1, G2 whole inverse, that is asymptotically stable, that means at least starting from zero frequency and then to very high frequency, it will always contribute finite gain. The way I explained the H infinity norm by the Bode plot, if it is a seesaw case, then your I plus G1, G2 whole inverse, simply 1 by 1 plus G1, G2, it would be another transfer function. If it belongs to RH infinity, its H infinity norm would be finite. That means for all frequencies, it will like give you like the finite values, right? So if it is so, then we are done. Only thing that is you have to check that what is the situation at infinite point. Infinite means you see that is here we are taking the inverse, right? I plus G1, G2 whole inverse. If it happens that suppose both G1, G2 are biproper, that means G1 infinity into G2 infinity, that is it would be non-zero, and in some cases, if it is equals to -1, then what will happen?
minus I.
If it is CISO, then it would be suppose in the 1. So then it is 1 plus. That is what I wanted to mean. That is the example which we considered, 1 minus s by 1 plus s. Right? That is the plant we considered, and feedback, we consider the unit negative feedback, right? So that is in terms of that if I write this is G1 and then G2, we can write simply 1. Right? And now, so what will happen? That what is your G infinity? G1 infinity? It will be -1? -1 or +1? -1. Because if s goes to 0, that will give you DC gain. But if it is infinite, it will be -1. Is it not? Or is it doubt? That is, finally you will have to put s, limit s tends to infinity. It will be -1, right? So G1 of infinity is -1, and G2 of infinity is the real number, so it will be 1. So G1 infinity into G2 infinity, that would be -1. Then what is the situation of 1 by 1 plus G1 G2? That will be the difficulty. So that's why whether a system is well posed or not, just you check whether this I plus G1 G2 inverse, it exists at infinity. That is a very short checking condition. Why that is coming? You can easily argue that is, sir, why you are only considering at infinity point? What is the situation? There are many other finite frequency point where the situation would be. But that is already when you were designing the controller. That is our job. That is I plus G1 G2 whole inverse, that will belong to R infinity. Because otherwise, ultimately, that is this internal stability will fail. So this I plus G1 G2 whole inverse. So if the inverse exists at infinite frequency, then we are done.
So here we have found out G1 infinity and G2 infinity separately, and then we have substituted there. So but if we first find out 1 by 1 plus G1 G2, and then we, whatever comes the expression, there we substitute infinity.
The same thing will come. Because when the expression here individually I am finding out and then I am putting, that is here, that is ultimately, that is, you suppose this is, this denote this one by t, then what will happen at t of infinity? T of infinity means all the frequency domain quantity, that is, you have to put the limit provided they exist. Now in that case, it is not going to exist, right? So that's why I wrote separately. When we write a limiting notation, before that you will have to check whether the limit exists or not. Here suppose if you have to write that is limit s tends to infinity 1 by 1 plus G1 G2, this doesn't exist, right? So why that doesn't exist, that is the reason we are talking about. And then here what is the problem would happen, that is if you once again go back to the U1 and U2, then at all finite frequencies the situation will go smooth, no problem, but at the infinite frequency it won't exist. You can say about sir, with infinite frequency उसमें कुछ झंझट नहीं है, but it is in frequency domain. The same thing when you will like translate back to time domain, then you know that the very high frequency means that is the transient, and very low frequency means that is the steady state. So then at the infinity point it doesn't exist, means there will be a break during the transient condition. So that's why infinity point is equally important. If a signal has to exist in time domain, and if you decide to carry out the analysis in the frequency domain, then you have to check for the entire frequency range. Not only in finite frequency, you have to check the infinite frequency as well. We will talk about it more later, but at this moment just I gave you the concept of that well posedness and especially the condition and the situation, that is if it is doesn't exist at infinity, then what the situation will be. Like that is like if I use a value, say for example this W1, that is a reference signal, so this is suppose R and we are going for unit step, so this will always be one, right? And then suppose here the W, there is no disturbance, so this part is fine, so there is completely 0, so now Q1 will be this one. Now you see that is there is unit step, shouldn't be any problem, but all of a sudden when it goes to very high frequency or at theoretically at infinity, there it explodes, but that is not a real phenomenon, right? Asymptotically stable system, if everything goes fine, it should not explode. That is, can you think about the situation that is in the real time, what is going to happen? That is, you see that is W1, it is a bounded signal, it is just a simply unit step signal, and output U1, that means the input here, this signal basically, this is a unit step, and then here at omega equals to infinity, that is it is going to be infinity, that means that unit step signal that is going to be multiplied by a very high gain, that is absurd. So that is the well-posedness problem. And in that example, what did you see last day? That is, we started with a biproper system, but ultimately the closed loop transfer function has become improper. So that is the well-posedness issue. So that is in the from one aspect we understood, that is a biproper system, it has become improper in closed loop. And then the reason I discussed with respect to the solution of differential equation. Now you have seen the reason why it is happening. Okay? You think further about it, and then if you get some other points, please feel free to share. Is it fine up to this much? Okay, or you can stop.